Have you ever stopped to think about the invisible magic that powers, well, everything? It's in your phone, your car, literally everywhere. It's this unseen engineering managing the flow of electricity. Today, we're going to pull back the curtain on one of its coolest tricks.
Okay, so think about this. You're in your car, right? And you plug your phone in to charge. Your car's battery is chugging along at about 12 volts of DC power. But your phone, it only wants 5 volts. Your laptop, that might need 20. So how in the world does that one 12-volt battery power all these different gadgets without, completely frying them or not giving them enough juice?
Well, the answer is just so elegant and clever. It's a brilliant little circuit called a DC to DC converter. Seriously, this thing is the unsung hero hiding inside pretty much every piece of tech you own. Its whole job is to take one DC voltage and efficiently transform it into a totally different one.
All right, here's our game plan. We'll start with the core problem. Then we'll meet the boost converter and its secret weapon, the inductor. After that, we'll check out its super versatile sibling, the buck boost, see what's actually inside these things, and then tie it all back to the world around us. Let's get into it.
So, here's the fundamental puzzle, right? We live in this world of, well, voltage mismatches. You've got one battery, one solar panel, one source of power. But inside your gadgets, you've got dozens of tiny components, processors, lights, sensors, and every single one of them is screaming for its own specific, perfectly stable voltage. That is the exact challenge these converters are designed to solve.
Okay, let's kick things off with a real classic, the boost converter. And its job is, well, it's right there in the name. It takes a lower DC voltage and just boosts it up to a higher one super efficiently. It's the perfect solution for, say, when your 3.7-volt phone battery needs to power something that's asking for 5 volts.
And what's really cool is that the circuit itself is surprisingly simple. Just 4 main parts. You've got the inductor, which is kind of like a temporary battery that stores magnetic energy. There's a switch, which is like a lightning-fast gatekeeper, opening and closing thousands of times a second. The diode, that's just a one-way street for electricity. And finally, the capacitor acts like a little water tank, smoothing out the voltage so it's perfectly steady for whatever it's powering.
All right, now we get to the really cool part, the secret sauce. It all comes down to the inductor, and this one fascinating, unbreakable rule of physics that it has to obey. This is the key to the whole thing.
And that rule is called the zero average voltage rule. It sounds a little technical, but the idea is simple. Over one full repeating cycle, the average voltage across that inductor has got to be 0. Think of it like a seesaw. If it goes up with positive voltage, it must come down with an equal amount of negative voltage to get back to level. It can't just keep piling on energy in one direction forever, it has to balance out. So, how does this rule let us crank up the voltage? It's all about a two-step dance. Step 1. The switch flicks on. The input voltage flows right into the inductor, and it starts charging up with energy, storing it in its magnetic field. You can see its current rising. Then, step 2. The switch flicks off. The inductor instantly tries to keep that current flowing. To do that, it unleashes all that stored energy, creating a voltage spike that adds to the original source, forcing the output voltage to go higher.
And this is the perfect way to see that zero-sum game in action. The amount of volt-seconds it gets while charging up, that positive area, has to be perfectly canceled out by the volt-seconds during the release, that negative area. So here's the trick. If you make the release time really, really short, then to keep the areas equal, the release voltage has to be really, really high. By just playing with the timing of that switch, you can precisely control how high the output voltage goes. It's brilliant. Okay, so the boost converter is great. It's a specialist. But what if you need more flexibility? What if you need a tool that can do it all? Well, say hello to the buck boost converter. This thing is the true Swiss Army knife of power electronics. And this is where things get really wild. With just a clever rearrangement of those same basic parts, the buck boost circuit can do 3 amazing things. It can step voltage up, just like the boost. It can step voltage down, and it can do something mind-bending. It can actually flip the polarity, turning a positive voltage into a negative one. This opens up a ton of new applications. And how do you control all this magic? It all comes down to this one simple little formula, and it's all about D, the duty cycle. That's just a fancy way of saying the percentage of time the switch is on compared to when it's off. By tweaking that one timing knob, an engineer can get basically any output voltage they want. That is some serious control.
So, is there a catch? Of course there is. Think of it this way. The boost converter is a specialist. It does one thing, and it does it really well. The buck boost is the jack of all trades. But all that amazing flexibility comes at a cost. See, with the buck boost, all the energy has to go into the inductor first before it gets to the output. This puts way more stress on the components, which can mean it's not as efficient and might cost more to build.
Okay, up until now, we've been talking about a switch like it's a little light switch you flick. But in reality, it's not a mechanical thing at all. It's an absolute marvel of modern engineering. So let's peek behind the curtain and see what's really doing all this fast-paced work.
Yeah, definitely don't picture a light switch. These are solid-state semiconductor devices, no moving parts. They're basically super-powered transistors that can open and close a circuit with insane speed and precision. We're talking hundreds of thousands, sometimes even millions of times every single second. It's mind-boggling.
And in this world, there are two big players you'll hear about, the power MOSFET and the IGBT. They're like different athletes for different sports. The MOSFET is the sprinter. It's the speed demon, perfect for really high-frequency applications. Plus, it has this cool built-in body diode that acts like a safety valve. Then you have the IGBT. That's the weightlifter. It's built to handle huge amounts of power for big stuff like electric motors, but it's a little slower and usually needs a friend, an extra diode, to help it out.
Okay, so we've been geeking out on the theory here, but let's zoom back out. Why does any of this matter? What's the big deal about this little circuit? Well, it's simple. Without it, our modern world just wouldn't work.
I mean it. These things are absolutely everywhere. They're inside your phone, carefully managing its battery. They're inside your laptop, juggling a dozen different voltages for the screen, the processor, everything. They're the reason we have super efficient LED lights. They're in your TV. They're in the giant data centers that keep the internet running. They are everywhere.
And looking forward, they're even more important. Electric cars are packed with them, managing the massive battery pack and powering everything from the main motor right down to your radio. They are the crucial handshake between a solar panel and the power grid. You'll find them in wind turbines, in life-saving medical devices, and in the crazy advanced systems that take us to space. When you think about it, the story of the DC to DC converter is just a perfect example of how one really clever solution to a fundamental problem can completely change the world. It just unlocks decades of innovation. So the next time you pick up your phone or turn on a light, just for a second, think about that silent, unbelievably fast dance of energy happening inside. It kind of makes you wonder, doesn't it? What amazing new technology will these tiny, magical circuits make possible next?